This problem is a very important one to understand because something very much like it happens on the exam. Um, Actually, it's more like this one is the most important. The others are kind of running up to it and an application of it. Um, I'll do a couple from the beginning just to give the idea. Um, so just read it off. You've got a table, but part A wants the derivative of 3 times f of x. It's just applying the rules for derivatives, the simple rules for derivatives, like when you have a constant times a function, when you take the derivative of that, then, right, that's all that's going on here. Then you're allowed to take the constant times the derivative of the function, right? Constants come out. Constants can be factored out to the front, I guess is the way to say it. And then, of course, we want to convert this to the prime notation. This is just 3f prime. But then, of course, we're evaluating at 2, right? Sometimes we use the notation vertical line 2 to mean evaluate at 2. That's a little non-standard, so I'll just leave it unsaid until the very end, f prime of 2. And then that's just, look it up in the table. You want f prime, and you want 2, so it's 4/5. So it's 3 times 4/5, right? Of course, 12/5. I don't have to write that because you've got the answer showing. Right, same deal here in B. What's the derivative of a sum? It's the sum of the derivatives. So you'll be taking f prime of 3 plus g prime of 3. How are you going to figure out f prime and g prime of 3? Well, f prime and g prime on the table, right? And use 3 for the row. F prime of 3 is 3 pi, g prime of 3 is 5. So that's where the 3 pi and the 5 come from. F of x times g of x, be careful. Remember, there's a product rule. So the product rule means that that's a complicated answer. F prime times g plus g prime times f, right? So the product rule is going to get you a mixture of f and g and f prime and g prime, all evaluated at 3. So you're going to use the bottom row again. D is even harder because it's the quotient rule. So that one's got some kind of difference on top with one derivative in each product and then some squared on the bottom. Crazy rule. But again, when you plug in the values, this time at 2, using the first row, you'll have all those fractions will boil down to 27 to negative 16 to 27/5. E is the one I'm really going to focus on here, right? This is sort of classic chain rule stuff. This is really asking, what is the derivative of f? What's the derivative with respect to f when f is a function of something other than plain old x, right? F is a function of g. So f is like written as a function of g. It's like, if f is the function cube, g might be the function sine. So together they make sine cubed. How do you do complicated derivatives, more than one step derivatives? Chain rule. So that's what goes on here. The chain rule is written as the derivative of a function of another function is, yes, you take the derivative of the outside function, the f, right? You take that derivative, you apply it to the old g, but you have to multiply by the chain term. And the chain term is the derivative of the inside function, outsides and insides. There's the inside function, but there's the derivative, okay? So this is being evaluated at 2, so you have to go through a couple steps here, right? You have to take f prime and evaluate it at g of 2. That's the original function, untouched, g of 2. Sorry about that. And then g prime, right? That was the chain term, the derivative of the inside function, g prime of 2. Now you can look things up on the table, right? That's f prime evaluated at g of 2. What is g of 2? Well, here's the g column, here's the 2 row, so the answer is 2, right? Times g prime of 2. Well, g prime of 2 is the g prime column. The 2 row, that's negative 4 times negative 4. And of course, we need one more step. We need to know f prime of 2, right? F prime of 2, okay, f prime column 2, 4/5. So that's why the answer is what it is. It's 4/5 times negative 4. Again, the ending is just read off the table, right? It's all read off the table starting here, but you can't get there unless you know the chain rule. This is just the chain rule applied symbolically, let's say. Most people know it verbally. The derivative of a complicated function or function of another function is the derivative of the first function applied to the complicated inside stuff times the chain term, which is the derivative of the inside stuff. So there's an inside-outside sort of almost poetic way to remember it, but this is really demanding that you know the symbolic way. And that's why they give you a table so that you can't go inside-outside. That's why they evaluate it, a number. So you can't just go inside-outside and write things in terms of x. It's got to be numbers at the end. F is the same. You can really consider this the square root of f of x. So that's sort of like s of f of x, where s is the square root. So, chain term again. The other way to do it is just treat f of x, take the derivative of f of x to the power 1/2. And again, something to the 1/2 power. I know how to take the derivative, 1/2 in front, decrease the power by 1, and then, of course, multiply by the derivative of f. It's a chain term thing again. So this will lead to something a little bit more complicated, right? When I take the derivative, it's 1/2, as I said. I'm treating that as the power 1/2, right? Ignore the square root and turn it to 1/2 power. So the derivative is simply a matter of, okay, I bring the power down, I decrease the power by 1, so 1/2 minus 1 is negative 1/2. And then, of course, you always have to take the derivative of the inside. That's the whole idea of the chain rule. Right? And then we're evaluating all this at 2. So now it's just a matter of plugging stuff in. And, of course, you've got negative 1/2 power. That's 1 over the square root. A lot of messy stuff, but it's all arithmetic now. Just like over here, it's basically all arithmetic. Same thing here, right? You plug in 2, you do the arithmetic, you're fine. What was the main point? You got to do the chain rule right from the beginning.